Next, we'll go through all of you and come back and have questions. Our next speaker is Dr. Christof Koch. He's the Chief Science Officer at the Allen Institute for Brain Science, where he is leading a 10-year large-scale effort to build brain observatories to map, analyze, and understand the cerebral cortex. Dr. Koch has authored more than 300 scientific papers, 5 books, and 8 patents. His latest book is Consciousness: Confessions of a Romantic Reductionist. That sounds fascinating. Yeah, it's a great title. Previously, Dr. Koch was a professor of biology and engineering at Caltech. Thank you for joining us.
Thank you very much, Jim. Yeah, and consciousness will be the topic that I choose to focus on. But first, something about the Allen, who we are. So we're an independent non-profit research organization that supports basic neuroscience. We were started in 2003 by Paul and Jody Allen. We're dedicated to open science. So what we've done over the last 10 years, we've made a number of atlases, 6 atlases to be precise, available. They show the distribution of genes, of all the 20,000 genes in the developing mouse, the adult mouse, the developing non-human primate, the adult human primate, the developing human, and the human brain. It's a couple of petabytes data, and all of it's available freely without any commercial or without any restriction whatsoever. In fact, all of this data is available prior to publication. We're very much a project-focused, milestone-driven, so we are somewhere between biotech and academia. We have large-scale, it's not large with respect to CERN, but it's large with respect to academic universities. So we'll have a couple of hundred people focusing on 1 or 2 projects, focusing on the mouse and on human. Okay, that I wanted to skip. So our 10-year vision is focused on a cell type similar to the announcement that Terry just referred to by the NIH yesterday. We've focused on cell types. So the great discovery over the last 20 years in neurobiology has been that they're not just 2 types of cells, but there are hundreds of different unique cells that have unique identities and unique connectivities. And in order to understand the brain, we really need to understand these individual cell types, both in animal models such as the mouse, as well as in human. And this is what we seek to do by building these large-scale observatories where we can observe large-scale neural activity in real time across the entire brain. There are sort of 5 ethical considerations that we have identified over the years, and I want to focus on the last 2 because I think there's some really new emerging ones that I would urge the Commission to consider. So first of all, we're doing invasive experiments in behaving rodents, and so you need an eye of Cook, and you have the usual ethical consideration that we all know about. We do a lot with human material, so we work with postmortem human brain material, so that the issues of identification and privacy. We work with prenatal human tissue, the same issues of privacy and what to do if any of the information allows people to identify the donor. Then we use surgical excised tissue and then human stem cells that develop into large neural networks that raise potential ethical problems. So common to all of this use of human tissue is informed consent. There needs to be an adequate communication of benefits and risks of research for the donor and his or her immediate family. There is the issue of privacy or loss of privacy. The public availability of genetic information throughout the brain could potentially lead to a loss of privacy and potentially that you would be able to identify the donor and any associated pathology. So there has to be concern about that, and there has to be concern about communication with the next of kin and other surviving family members if that happens. There are sort of 1 or 2 unique ethical issues that come up here. So what we're doing now, it's only rarely done during neurosurgery, particularly for tumor surgery as well as for epileptic surgery. Sometimes the neurosurgeon, in order to access deep tissue, has to remove overlaying parts of the brain, which are healthy. So in principle, you can take that piece of tissue. It can be as small as the tip of a finger. It can be as big as a finger, or sometimes it can be the entire medial temporal lobe or some other part of the lobe. So it can be as big as a fist. So this tissue, in principle, can be dropped, and we're doing that now into sort of into a bath, a cool bath, and then in principle you can cut it and you can do all the standard electrophysiological experiments on it, including 2-photon calcium imaging. So the advantage of it, you have a piece of brain that used to be in a living donor that you can now study. It's a human brain, it's not an animal brain, so you can study its properties. Which is of course extremely interesting because usually, for obvious reasons, we don't have access to the cellular level resolution in humans. You can potentially cultivate these to have a so-called chronic culture. Nobody's done that yet because of technological problems. So in principle, you can keep this tissue alive right now for under a day, but in principle, if you turn it to long-term culture, you could keep it alive for at least days. Typically, there's no organized large-scale neuronal activity in this tissue anymore, so it's not active by itself. So typically what you have to do, you have to inject current in order to observe electrical behavior. Now, we all know, we're all familiar with human stem cells, and we're doing since a number of years in research on human stem cells, either from approved human stem cell lines that have been approved by NIH, or from a so-called adult stem cells, where we can take from any volunteer, we can take a snippet of skin cells and de-differentiate them, and then add 4 transcription factors and turn them into neurons, into neuron forebrain neurons, cortical neurons, for instance. So now in principle what we can do, and what other people have done, in particular a spectacular publication that made the headlines coming out of Vienna by the group of Knoblich a couple of months ago, where they developed so-called organoids. So these are tissues, this is human tissue now, from in this case it was the H9 cell line, but in principle you can do this from any volunteer. So you now have in a dish a couple of square millimeter of cells that showed layered organization, similar to what it is in our cortex, some of them showing electrical activity. This for me raises, so my expertise, what I've worked on over the last 20 years is the physical and the neuronal basis of consciousness. So here potentially there's this ethical issue that we may have 1 million cells or 10 million cells, and in future maybe 50 or 1 billion cells, right? It's just a question of getting the cultural condition right. You have to cultivate them in a 3-dimensional medium. And so if you get electrical activity, if you get spontaneous electrical activity in this tissue, as sometimes you can obtain, the question we have to begin to ask ourselves, at what point does sentience emerge? At what point does it feel like something to be this network? That's after all what consciousness is. It feels like something to be conscious. And do we have any, right now there's nobody thinks about this. Most people think this is just, this is too far out, but I think it's time to think about it. What sort of electrical activity? We do know in healthy people, or we do know in patients, some of the electrophysiological criteria for consciousness. There have to be particular types of waves, theta oscillation, gamma oscillation, ignition at P300, etc. There's a whole set of, there's a whole range of electrophysiological criteria. The question is, we may not see the same criteria in this tissue because obviously it's grown in a very different way, but still we need to begin to think about a question of sentience in a dish. And with that, I'd like to thank you.
That's dropping a very provocative thought. Thank you. I'm sure we're going to get back to that.